Hi students, today's topic of our discussion is source transformation. That is, today we are going to discuss about source transformation. So before going to the source transformation, let me introduce what is a source. So all of you might have heard about current source and voltage source in your last semesters. Okay, that is, you are familiar with voltage source and current source, and these are the two sources actually we are using in electrical network. So in general, we can say, or we can define the source as an active network element. That is, the source is an active network element which is used for energizing the electrical network, or in other way, it is, this source is generating the electronics energy or the electrical energy. That is, source is nothing but an active network element. It is used for generating electric energy, and mainly the source can be classified into two, and they are voltage source and current source. Okay, and this figure shows the classification of the source. The source can be either a voltage source or a current source, and again both the voltage and current source are divided into ideal voltage source and practical voltage source, and also ideal current source and a practical current source. So let us see what are these ideal and practical sources. So let's start with voltage source. So voltage source is a two-terminal device. It's a two-terminal device, and which is used for supplying the voltage to an electrical network. And at the same time, the voltage which is supplied by the source will be constant at any time of any instant of time, and this value of voltage is independent of the current which is drawn from the voltage source. Okay, that is, voltage source is a two-terminal device and whose voltage at any instant of time is constant, and it is independent of the current drawn from it. That means whatever be the current taken from this voltage source, the voltage which is supplied by the source is always constant, and this kind of voltage source is termed as the ideal voltage source. That is, this statement is true only in the case of an ideal voltage source. That is, in order to make the voltage which is supplied by this voltage source is constant, we need to make the internal resistance of the voltage source as 0. So we can say that in the case of an ideal voltage source, the internal resistance is 0. So when we think about the practical cases, it is not possible to construct a voltage source with internal resistance 0. Because of this, all the sources practically available is having an internal resistance, and therefore that is not considered as an ideal voltage source. So the main difference between the ideal voltage source and the practical voltage source is, in the case of practical voltage source, there should be some internal resistance for this voltage source. And so we can say that the ideal voltage source is a concept. And this figure indicate the symbol which is used for the representing the voltage sources. Here we have two different symbols. We can use either the first symbol or this symbol. Both are same. So here we can see the two terminal. One terminal is represented as A and the other terminal is represented as B. And usually we are using this symbol for representing a DC voltage source. Okay, and that is about the voltage source. And now let us see what is a current source. So similarly, the current source, ideal current source is again a two-terminal network, a two-terminal element which supplies the same amount of current with the same amount of current to a load irrespective of the value of the load resistance. That is, whatever be the value which is connected across this current source, the same amount of current will be supplied by the ideal current source. So in order to maintain this property, that is, even if we are connecting a high load resistance, in order to maintain the current constant, the internal resistance of the current source should be infinity. So as you know that in practical, it is not possible to construct a current source with a resistance, infinite resistance. So all the practically available current source is having an internal resistance which is less than that of infinity. And now we can say that if the internal resistance of this current source is much higher, we can approximate that practical current source to an ideal current source. So this figure represents the two different symbols which we are using for representing a current source. And the arrow in this symbol represent the direction of the current flow. Okay, so that is about the current source and voltage source. But our topic of discussion is not what is current source and voltage source, it is the source transformation. So that term source transformation is nothing but this sources, that is the voltage sources and current source, are mutually transformable. That is, we can transform the one kind of source to the another kind of source. That is, in specific, we can transform the voltage to a current source or current source to voltage source. That is, voltage and current source are mutually transferable. So in this section, we are discussing how we can transfer a current source to a voltage source or a voltage source to a current source. So as I told you, in the case of a voltage source or a current source, there exists an internal resistance. So the practical current source and voltage source can be represented as shown in the figure. So this figure A shows a practical voltage source. Here you can see a voltage V which is placed in parallel with a series resistor, and this resistor is nothing but the internal resistance of the voltage source. So this is the representation of a practical voltage source. Here V represent the voltage value and RV represent the internal resistance of the voltage source, and this ILV represent load current which is supplied by this voltage source. Okay, and similarly, this is the representation of a practical current source. A practical current source can be represented like this. That is a current source with a internal resistance parallel with this one. Okay, and this here the internal resistance is represented as Ri. So this is the common representation of a practical voltage source and a practical current source. Okay, now just we imagine a load resistance RL is connected across this terminal XY. So this represents a voltage source, practical voltage source, and we are connecting a load resistance RL across the terminal XY. And similarly, in the case of this current source also, we are connecting the same RL across the terminal XY. Okay. So because of this load resistance, some amount of current will flow through this load resistance, and that is known as the load current. So in this case, ILV is the current flowing through the RL, and in the case of current source, ILI is the load current flowing through this RL. So now let us see how we can find out the value of this current which is flowing through the load resistance in both the case. Okay. So in this case, that is in the case of voltage source, the internal resistance RV and the load resistance RL are connected in series. So the same amount of current will be flowing through both this RV and RL, and you can find out the value of the load current. That is the load current is same as that of the current which is flowing through RV and RL in this case. So ILV can be found out by using the Ohm's law, that is I is equal to V by R. Okay, here R is the total resistance RV and RL. So we can find out the load current ILV is equal to V divided by RV plus RL, where RV is the internal resistance of the voltage source, and RL is the load resistance. And similarly, for in the case of this current source also, we can find out the load current which is flowing through this RL. So we can use different many methods for finding the value of this ILI. So here these two resistors are in parallel. This RI is connected parallel to this resistor RL. Okay. So this is the total amount of current, and this current will be split into two, and some amount of current will be flowing through this path, and some amount of current will be flowing through this path RL. So the current which is going through this RL is termed as the load current ILI. So these two RL and RI are in parallel. So in these parallel branches, we can find out the current. Like suppose if you want to find the current which is passing through this RL, that is equal to the total current supplied. Here the total current supplied is I, that is multiplied with the resistance of the branch which is opposite to that of the resistance which we need to find out the current. So here we have to find out the current through this RL. So the opposite resistance of the opposite branch is RI. So that is this total current multiplied with this Ri divided by the total resistance. That is sum of total resistance is nothing but sum of all the resistance used. So Ri plus RL. So we can write this ILI is equal to the total current I into the resistance of the opposite branch Ri divided by Ri plus RL. Okay. Now all these things I explained already. This ILV represent the load current in the case of voltage source, and ILI represent the load current in the case of current source, and I and V are the current and voltage. RV and RI is the internal resistance of voltage source and internal resistance of the current source respectively. Now let us see how we can transform the one source to another. Okay, suppose we want to transform this current source to a voltage source. Okay, that is this current source consists of this current value I and the parallel resistance Ri. So we need to transform this into a voltage source. Then when we transform this into a voltage source, it should have a voltage source with a series resistance. Okay, and in this connection we can see that because of this load current, there exists a voltage drop across this RL. Because of this load current, there exists a voltage drop across the load resistance RL, and that voltage drop is nothing but the RL multiplied with the load current. And similarly, okay, and similarly in the case of this voltage source also, here exists a voltage drop across RL because of this load current ILV, and that voltage drop is equal to the resistance multiplied with the current. Now we are going to transform this particular current source to a voltage source. That means instead of this current source, we are going to place a voltage source here. So when we place a voltage source here, the value of the voltage drop across this RL should be same. It should not change. If it change, means that all the parameter will change. That is, it will affect all the parameter. So it should not affect the voltage drop across RL. And suppose we are changing this current source with the voltage source shown here. That is, we are replacing with this voltage source. So here this voltage source, the load current is ILV. So in order to maintain the same voltage drop across RL, this ILV should be equal to ILI. So that is the condition to be satisfied when the source is get transformed. Okay, that is, when we transform this current source, we need to ensure that the voltage drop across this RL should be same. It should not be changed. So in order to maintain this voltage drop across RL constant, the load current which is generated by this voltage source should be same as that of the previous case. That is, ILV should be equal to ILI. ILV should be equal to ILI. So that is the condition required for the source transformation. So therefore, we can equate the load current for the voltage source and load current for the current source. So when we equate, we can write this V divided by RV plus RL. This is the equation for the load current due to voltage source, and this is the equation for the load current due to current source. Now, again, just we are going back. The voltage across this terminal X, Y, in this case, that is in the case of this current source, is nothing but the current I multiplied with this Ri. That is V is equal to I into Ri. So when we change this into voltage source, this I into Ri should be also equal to this V. Okay. So in this equation, this I into Ri can be replaced with V. So finally we can write V divided by RV plus RL should be equal to V divided by Ri plus RL. So here the numerator on both sides of the equations are same. We can cancel it out. So in order to maintain this equality, this RV plus RL should be equal to Ri plus RL. That is, in both the case the numerator is same. So in order to maintain the equality, the denominator should be equal. So we can write this RV plus RL is equal to Ri plus RL. Here in LHS and RHS we have RL, we can cancel it out. So finally we can write this RV is equal to Ri. And what is RV? RV is nothing but the internal resistance of the voltage source, and Ri is the internal resistance of the current source. So if you want to transform a current source to a voltage source or a voltage source to a current source, the internal resistance of the current source should be equal to the voltage source or vice versa. That is the main condition we have to satisfy when we do the transformation. So the internal resistance of RV should be is equal to Ri. So therefore, for any practical voltage source with voltage V and the internal resistance, it can be replaced by a current source I with the internal resistance in parallel with the current source. So how we can transform a voltage source to a current source or a current source to voltage source? So this figure represents that. So here we have a voltage source, and this can be transformed to a current source as shown here. That is, just now only I told, when we transform the current source to a voltage source or the voltage source to a current source, the internal resistance of both the source should be same. So when we transform this voltage to current source, the internal resistance should be same. So the same R should be placed here, but it is parallel with the current source. And how we can find out the value of this current source? That current source is nothing but Vs divided by R. So this is our circuit. We need to transform this to a current source. So already we know the value of Vs and a resistor R. So when we transform to current source, the resistance which is parallel to the current source is equal to or same as that of the resistance here, and the value of the current source can be found out by using the equation Is is equal to Vs divided by R. And similarly, for transforming a current source to voltage source, again the value of the internal resistance should be same. So the same R can be used here, and the value of this voltage Vs is equal to Is into R. So in that way we can transform a voltage source to current source or a current source to a voltage source. So finally, as a conclusion, if in an electrical circuit or network, if there exists a voltage source series with a resistor, that is, in a circuit if there exists a voltage source series with a resistor, that is, a voltage source is connected in series with a resistor, then that combination can be transformed to a current source with a parallel resistor. So that is the condition. When we can transform a voltage source to a current source, if a voltage source is connected in series with a resistor, then that combination can be transferred to a current source with a parallel resistor. Similarly, if there exists a current source with a parallel resistance, then that combination can be transferred to a voltage source with a series resistor. And the equation for finding out this Is and Vs is like this: Is is equal to Vs divided by R, and Vs is equal to Is divided by R, and there is no change for the resistance value. Okay. So now let us see one example. So here we have a question: find the current I through the 5 ohm resistor shown in the figure using source transform. So it is clearly mentioned you have to find out the value of this I which is flowing through this 5 ohm using a source transformation. So we have other laws there, that is Kirchhoff's law, Kirchhoff's voltage law, Kirchhoff's current law, and Ohm's law, etc. are there. But here it is mentioned that you need to use the source transformation. Okay. So let us see how we can do it. So here we have a current source and a voltage source. So if there exists a current source with a parallel resistance, that we can transform to a voltage source, and if there exists a voltage source with a series resistor, we can transform that to a current source. So here we have a voltage source with a series resistor 5 ohm, and at the same time here we have a current source with a parallel resistance 10 ohm. So we can transform these sources. So first let us start with the current source. Okay, you can start with any of the sources. You can start with either voltage source or the current. So for the time being, I am starting with the current source. Okay. So when we replace this current source with voltage source, the series resistance should be same as that of the resistance which is connected parallel here. And value of the voltage is nothing but V is equal to I into R. Okay. So the first step 1 is current to voltage source transformation. That is, this current source is transformed to a voltage source. So in order to transform, first we need to find out the value of V. That V is nothing but the I into R. That is 1 multiplied with the 10, that is equal to 10 volt. So when we replace with the voltage source, it will be like this. So we replace the voltage source with a series resistor, and the value of the series resistor is same as that of the parallel resistance which is connected across the source, current source. So that is 10 ohm here. Okay. So one transformation we already made. Now in this circuit itself, we can make some made some simplification. That is, here we have two resistors 10 ohm and 5 ohm. These two resistors are in series. Okay, that we can convert it into a single resistor. So before that, let's go for the second step. The second step is voltage to current source transformation. Okay, so here we have two voltage source, 10 volt and 10 volt. In one case, it is connected with a 5 ohm resistor, and the second case, it is connected in series with the combination of these two, that is 10 ohm and 5 ohm. So it is combined together to get a 15 ohm because this is in series. So here it is mentioned as 15 ohm. So just for clearly understanding this, I just redraw the circuit like this. So just to identify easily that this 5 ohm resistance is series with a 10 volt. So I placed this 5 ohm here, 5 ohm, I placed the 5 ohm over here, and this also the voltage source I placed over here, just to by seeing we can identify that these are in series. Okay, now we are going to transform these two. That is, we are going to transform this voltage source and this voltage source to a current source. Now, when we transform this current source to, this voltage source to a current source, the resistance which is placed in parallel with the current source should be equal to the resistance in series with this voltage source. Therefore, no change for this 5 ohm resistor, and similarly there is no change for the 15 ohm resistor as well. So in this case, we need to find out what is the value of the current source. So value of the current source can be find out by using the I is equal to the voltage divided by resistor, that is 10 divided by 5, that is equal to 2 ampere. And similarly, in the second case, the I is equal to 10 divided by 15, that is equal to 2 by 3 amps. So these two sources can be replaced with a current source as shown here. So this first source is replaced with a 2 ampere current source, 2 ampere current source with a parallel resistance 5, and the second voltage source is replaced with a 2 by 3 ampere current source with a 15 ohm parallel resistor. Okay. Now in this figure you can see that this 5 ohm resistor and this 15 ohm resistors are in parallel, and of course this 5 ohm is also parallel with this 2 resistor, but we are not going to disturb this 5 ohm resistor. Why? Because we are asked to find out the current which is flowing through this 5 ohm resistor. So we are not at all disturbing this 5 ohm resistance. That is why we are considering only these two resistors, this 5 and this 5, that is which is highlighted. So these two are in parallel, and at the same time this 2 ampere current is entering into this particular node X, and at the same time this 2 by 3 ampere is also entering into this node X. So we can combine these two current source also by adding this together. So this circuit can be redrawn as like this. Okay. That is, this 5 ohm and 15 ohm are in parallel. Therefore, the equivalent resistance is 5 into 15 divided by 5 plus 50, that is equal to 15 divided by 4. So these two resistance can be replaced with a single resistance 15 by 4 ohm, and the two current source can be replaced as a sum of these two, that is 2 plus 2 by 3, that is 8 by 3 ampere. So finally we get a current source 8 by 3 ampere parallel with the resistance 15 by 4 ohm, and we have already this 5 ohm resistance through which the value of I is flowing, and that is the value we need to find out. And the last step, or the third step, is again we can convert the current to voltage source transformation. That is, here we have a current source parallel with a resistor, so that also we can convert to a voltage source. Okay, that is, in order to find the voltage we need to do this calculation. V is equal to the I into R, that is I is equal to 8 by 3 here, R is equal to 15 by 4, and that value is equal to 10 volt. So V is equal to 10 volt, and the resistance which is going to place in series with this voltage source is same as that of the resistance which is parallel with the current source, that is equal to 15 by 4. So 10 volt is in series with the 15 by 4 ohm. Okay, and still the 5 ohm resistance are there without any change. Now you can find out the current I flowing through this resistor. Okay, so these two are in series, so the same amount of current will be flowing through both the resistor. So this I can be found out by using the Ohm's law relation, that is V is equal to I into R, or I is equal to P by R. Here we need to consider the total current, total resistance 5 by 4 plus 5. Okay. So total resistance here is equal to 15 by 4 plus 5, that is equal to 35 divided by 4. So current I is equal to 10 into, that is voltage into R. So I is equal to V by R, that is 10 divided by 35 by 4. So 10 divided by 35 by 4 is 10 multiplied with 4 by 35. So that is equal to 8 by 7 ampere. So finally we can find out, or we arrive the value for I, that is equal to 8 by 7 ampere. Okay. That is, the current through 5 ohm resistor is 8 by 7 ampere. So in this way you can find out the current, or you can find out the voltage also using source transformation. So here you have some quiz questions. So after this class you try to answer this quiz questions and submit. Okay, with this I am winding up this particular topic, and thank you all.